Okay, ladies and gentlemen, let's take a look. So what we're looking at is family of curves. If a parabola has the roots 2 and 4, we know that x equals 2 and x equals 4. The line before this would have shown factors like this. X minus 2, x minus 4 equals 0. Do you see that? Working backwards. Good. The equation of the quadratic could have been given as y equals. This would be in factored form, wouldn't it? This would be in expanded form, standard form.
Excuse the interruption. We ask that, with teachers' permission, those students that signed up for information on the Earning Credits in Italy program this coming summer, we ask that you move to the conference room off the forum. Thank you. So,
now what we have is, however, there are many parabolas that could have these roots. They will all be stretches, compressions, or reflections of each other. Some examples are going to be shown in the diagram. So a lot of people look at this and go, what is that? I don't know what's going on here. And it's very scary. Well, the truth of the matter is what I have. Now let me create this diagram for you. We said that we had roots x equals 2 and x equals 4. So as roots, that means that those are the values of x that will make the equation equal to 0. Those are real roots. They are distinct roots. Those are two different intercepts. Now, so what I am graphing is but hold on here. I could have any number in front of this. So even though this parabola satisfies the roots x equals 2 and x equals 4, so does this parabola. So does this parabola. Not even getting into the argument of, so does this parabola. You see what I'm saying? So we could have stretches and compressions, which is what that a value does, right? Or we could have reflections in that x-axis going up and down. And they all still have the same roots. We call that a family of curves. Everybody that has the same roots is part of the family. If we want to know a specific curve, we need a point on the curve. Okay? So notice all of these have these roots, these intercepts. If I want to be able to figure out which one I'm talking about, I also need another point on the curve. Not the intercepts, but another point. Question, Anthony.
Is there an infinite number of curves in a family?
Yep. Absolutely. Because of the coefficient, any real number could go in. There's an infinite number of real numbers. There's an infinite number of members in the family. Yes. So now let's look at this. This shouldn't be as scary anymore. So up here, this particular curve is supposed to represent 2x squared minus 6x plus 8, which you'll remember is the same as 2x minus 2, x minus 4. One's in factored form, the other one's in semi-factored form. I'll make it bigger. Is that good? This would represent just the parabola x squared minus 6x plus 8. This would be a horizontal, a vertical compression, so it's flatter. Okay? Here we have the reflection in the x-axis. So does this make sense now? It's not as scary, right? So this is a whole group. Look what it says here. I've got this thing on the side. That's a pain. I don't know how to get rid of that. Maybe I can. There you go. Goodbye. Okay, so all 6 graphs belong to the family of functions defined by. Now, you're not going to like this. They put a d out in front. What did I put out in front? Does it matter? Okay, that's important. It really doesn't matter. It's a variable, isn't it? It represents any real number that could go in there. So these are 6. We know there's much more than 6, right? But these are 6 of them. All where the value of d determines which of these functions we're looking at. Does that make sense? Okay. So to determine the equation of a specific quadratic, we need to know its roots and one other point on the quadratic. It's got to be another point. Okay? It's incorrect to say 1 point, because I already know 2 points. I know 2 intercepts. We good? Yeah, George. Absolutely. All right. So that's George going to the washroom. I'll flip over, and we will do example 1. Hi, George. And this is a live to air broadcast. Well, not really, but if you want to see who's in the class, I can. Oh, they're upside down, Ma. Okay, so this is actually a real live broadcast. Okay, you'll notice a lot of people have hands over their faces. We're not sure why. Oh, yeah, there it happens again. Okay, so that was fun. We'll do that again when they're not expecting. We'll do that when George comes in. When George comes back. Okay. So let's do something. Determine the family of quadratic equations. So I want the family with the following roots. Then, do you see the then? There's 2 questions. Then determine the exact equation for a parabola with the same roots, but passing through this point. There's 2 questions here. First the family, then the specific. So, let's go for it. First question, 1. Determine the family of curves with x equals 3 and x equals -7. Yes, question?
So when you determine a family, do you have to give a certain amount of examples in the family?
Actually, we're going to write it with a variable in front, which will represent all of them. Yeah, it's going to be cool. That's right. So do you see these roots? These are roots. That means now, I might have jumped a little bit. And I put a D in there. I might have jumped ahead a little bit. Let me go back. Do you see these roots? See how it says x equals 3? Would you agree with me that the step before that was x minus 3 equals 0? And would you agree with me that the step back here would be x plus 7 equals 0? Okay, so then what I did was I took these 2, and I said for the family, it would be y equals d, x minus 3, x plus 7. So do you see how I went straight to here? Okay, so I got a little bit extra over here to explain what's happening. So that's the family, where d represents, or d is an element of the real numbers. And what that means is that d keeps changing. Now, that's in factored form. If I wanted to put it in standard form, then I would simply do this. But that looks pretty weird, doesn't it? All those D's in there. So we would actually leave it like this. And that's the family. That's it. If I put in a 1, I'll get a particular No, so let's take a look. If I allow d to be 1, then it would go through x equals 3, x equals negative 7, and if d is 1, well, that's positive, right? So it would look something like that, if d equaled 1. If d equaled 2, then it would be a vertical stretch. So then perhaps it would look like this. Or if it was negative, it could look like that. Do we understand? So as d changes, the shape of that curve changes, either up or down, and skinny and fat. But to still go through negative 7 and 3. But we want a particular curve. The second question. But if we know that the point 2 comma negative 27 lies on the parabola, then we can sub in x equals 2 and y equals negative 27 to determine the d value. And you'll see that I'm quickly running out of room. But what that would mean is, remember how this was y, this is d, and this is x. I could either put it in here, or I can go back up and put it in here, depending where you think it might be easier. Oh, you can't see. There you go. So I could put it in here, or I could put it in here because they're equivalent. You know what that means, right? They give the same value. So I'm thinking it's easier to put them in up here. So what I would get is I would get negative 27, that's my y value, equals d, 2 minus 3, and 2 plus 7. And I got that by taking the x and the y and plugging them into here. Now, I am very quickly running out of room. Do you have more room? Okay, so if I attach a little sheet here, can I do this and you still have some room?
Yeah.
Negative 27 equals d minus 1 times 9. D is going to equal negative 27 divided by negative 9, which is 3. Okay, spend some time and look at that.
Sir,
Yeah,
can you also put it into the standard quadratic?
we said that, yeah. Yeah,
How come there's two equal signs?
oh, because I went across. I didn't want to go down because I ran out of room.
Oh, okay, so that would be like on another line.
Yeah. Or you could leave it like that. I will let you get away with little things like that.
Sir,
Yeah,
you're allowed to add more equal signs as long as it remains true for all three, correct?
yep. Okay, so I have my d value. So therefore my specific curve with roots 3 and negative 7 passing through 2 comma negative 27 is y equals 3x squared plus 4x minus 21, or 3x squared plus 12x minus 63. And I don't really care which form you put it in. Where did this 3 come from? It came from finding out the d value. So what we did was we took the family of curves and we took a point, we plugged it in, and it gave us the actual d value. And for terms of this video, I'm going to stop it here so I can talk to the class separately, and I'll come back with the next example.